Hi, welcome to the first of two videos that are going to deal with solving force problems. These will probably turn into an Ed puzzle because that's how I get people to watch things. So there you go. So we're going to go through 5 total problems, and hopefully this will be after you've taken the Google or the physics classroom reading quiz. I don't know if the equations are in this particular order, but these are the 3 big equations we're going to use with forces. So the first one is the acceleration of an object is directly dependent on the net force on that object and inversely dependent on the total mass of the system that's accelerating. So you should write these formulas on your formula sheet. This is the version that I like, A equals F net over M tote. You can rearrange that to look like this. And that, again, that is Newton's second law. A version of Newton's second law that's much more specific deals with the weight of an object, which I really like to think of as the gravitational force of an object, close to the surface of the Earth. Technically, this could be close to the surface of any planet, but on Earth, we're going to find, hopefully at the beginning of the week, that we've got, from our Force of the Earth lab, we're going to figure out what G is. So lowercase g is a gravitational field strength. Interestingly enough, if you look up here, this formula looks a lot like this. Net force, we'd measure in newtons. Weight, we'd measure in newtons. Mass is a standard unit of kilograms. Mass here has a standard unit of kilograms. Acceleration is meters per second, or meters per second squared. You could also write that down here, but actually you could also think of this as newtons per kilogram. So believe it or not, meters per second and newtons per kilogram mean the same thing when you go out and derive the formula for that, which I'm not going to do. The third equation down here is for friction. So we know we've got friction that acts on a lot of objects close to the surface of the Earth. And for 2 solid objects that are sliding past each other, we see this relationship. This symbol is the Greek letter mu, mu, and it stands for the coefficient of friction, and that's a relationship between the force of friction divided by the normal force acting on an object. Well, what the heck's a normal force? A normal force just happens to be the perpendicular force acting on an object. So if it's a surface, like a flat surface, oftentimes the normal force of the ground upward is equal to the weight of the gravitational force on the object sitting on the surface downward. So on a flat surface, many times you could figure this out by just using m times g. Sometimes when you're pushing down on an object or pulling up on it or something's being pulled at an angle, this would not necessarily be the same as the object's weight. So we have to be a little bit careful about that, and we'll go through some examples about that. Generally, we think of the coefficient of friction as being equal to these two. That is true for kinetic friction, which is when things are sliding past each other. For static friction, that coefficient is actually somewhat variable. So the maximum coefficient of kinetic friction times the normal force, and I don't know if that's, I always forget whether that's less than or equal to, so we're just going to put that down there as being equal at this point. But I do want you to understand that for static friction, when things aren't moving, the amount of friction can be variable. When 2 solid objects are sliding past each other, it's fairly consistent. And again, this is called the coefficient of friction. So I'm going to get ready and set up the first example, but keep those equations in mind.
Wow, it's filthy, and it's mine.
All right, this is a continuation of the video. So I've written down the first 2 problems up here, sample 0 and sample 1. So with sample 0, we've got a student who's sitting in a smooth rolling chair with a combined mass of 80 kilograms. So the student has some mass and the chair has some mass. The student then grabs a 10 kilogram fire extinguisher, just for fun, and turns it on and propels herself with an initial acceleration of 0.25 meters per second. By the way, sometimes you'll see this, meters per second is an acceleration. That means the same thing as meters per second squared. That's a little harder for people to think about as a unit. So sometimes I'll write it like this, and sometimes I'll write it like that. They mean the same thing. It also means the same thing as newtons per kilogram, believe it or not. But when we're talking about acceleration, we'll normally think about meters per second per second. At any rate, the question is what's the force applied by the exhaust gases of the extinguisher? Well, in this particular case, what we've got is Newton's second law. So we're looking for a force. So I'm going to go back to Newton's second law, and I'm going to say, actually I'll do this in color for dramatic effect. Say write the general formula down first. F net is equal to m tote times acceleration. All right, so we think we've probably got these things. We're just really trying to find the net force. We assume that it's a smooth rolling chair. We're going to assume that there's no friction involved, at least initially. So F net is equal to m total. How much is m total? Well, the student and chair have a mass of 80 kilograms, but the fire extinguisher, which we assume that the student is holding, has a mass of 10 kilograms, at least initially, before a lot of the gases are expelled. And this is asking about the initial acceleration. So we've got to take that total mass to be 80 plus 10 kilograms, or 90 kilograms. And the acceleration was 0.25 meters per second per second. So when we take 90 multiplied by 0.25, we get that the net force is equal to 22.5 newtons. Remember, the standard unit of weight is newtons, the standard unit of force is newtons. We don't use pounds for anything. Nobody in science would use pounds for things. In fact, a lot of times the engines in your car, even though they're rated in horsepower and torque is in Newton meters, or foot-pounds rather, they'll also have ratings in kilowatts and Newton meters. So in this case, 22.5 newtons is the thrust produced by, or the force produced by the fire extinguisher. Now the thing about that is if I was to ask you, would you predict that the real acceleration caused by this amount of thrust would be a little bit higher or a little bit lower than 0.25 meters per second per second? I think you would realize it probably would be a little bit lower. And the reason is, although we said this is a smooth rolling chair, in fact, there probably would be at least some friction. Wheels on chairs actually have a little bit of friction. If you were ending up going pretty fast, you might even have air resistance as well. So with that being said, that's your answer to number 0. For sample 1, we've got Batman. And Batman is accelerating upward at 3 meters per second due to the thrust of his jetpack. Batman has a mass, and we'll assume the jetpack's included in that, of 80 kilograms. Ignore air resistance. First of all, draw the free body diagram, and second of all, determine the amount of thrust force. A lot of times, even if you're not told to draw a free body diagram, I would make sure that you do that first because it's going to be helpful. And I'm going to draw that over here. So what I've got here, so I've got the force of gravity downward. On Batman. And we've got the thrust upward. Hopefully you realize that if the acceleration is upward, that the thrust has to be greater than the force of gravity downward. So I'll draw that like that. And you could call that thrust or force of jetpack, force of the thrust of the jetpack, things like that. And because it said we were going to ignore air resistance, capitalize Batman, we're going to ignore air resistance here. So this should be a bit longer than this. I'm not sure if that's really clear in the video, so I'll make it even a little bit longer. So it's definitely longer than that one. So now if I were to figure out the amount of thrust force, I'm going to write the general equation for Newton's second law down first, and then I'm going to go from there. So the general equation is F net equals m tote times A. Well, what forces are making up our net force? You can't just put this as thrust because that's not the only force in this situation. There's thrust upward and gravity acting on Batman downward. So I'm going to say thrust minus force of gravity is equal to m tote, 80 kilograms, times acceleration, which is 3 meters per second. So I really need to figure out how much that is. Well, if I go back and I use the second equation I showed you earlier, you can realize that the force of gravity is the same as the person's weight, and that's m times g. G on Earth is about 10 newtons per kilogram, or 10 meters per second. Technically, you could use 9.8 for that. I'm going to end up using, I want to be consistent with the written work that I give you. So I'm going to use 9.8. And that weight is 784 newtons. So now I'm going to go back here, and I'm going to say that thrust minus 784 newtons is equal to 80 times 3 is equal to 240 newtons. That would be easier to understand if we changed this to newtons per kilogram instead of meters per second squared. That's another way you can tell that they're equivalent. So I'm going to move this to the other side. Thanks, arithmetic. 240 plus 784. Okay, so that's going to be 984 plus 40. I think that's going to be 1024 newtons. And that would be the thrust on from the jetpack. So something like that. Again, that's example 0 and example 1.